Alright, so this is 10.2 matrix multiplication, which can be a bit of a bear, to be honest with you. In your vocabulary, we have what's called the identity matrix. An identity matrix, for let's just do a 2 by 2. It would look like this, 1, 0, 0, 1. Or if you did a 3 by 3, it'd be 1, 0, 0, 0, 1, 0, 0, 0, 1. These are what we call identity matrices. They're essentially like multiplying by 1. They are essentially the matrix equivalent for multiplying by 1. And they're also kind of that thing you guys were doing with the reduced row echelon form, aren't they? Now, a square matrix is simply a matrix with the same number of rows and columns. It's square, 2 by 2 or 3 by 3 or 4 by 4. All right, what does it mean to multiply a matrix by another matrix? So matrix multiplication is kind of interesting here, and we have a weighted grade example to kind of help you figure out what we would do here. So a teacher assigns final grades based on a weighted system. Students are graded on unit assessments, a semester project, and the final exam, each with different weight. The matrices below give the weights for each kind of work and the grades for two students, Oscar and Reagan. Now, if I want to know Oscar's grade, I would have to use this weighting percentile over here. So let's do Oscar's grade. Okay. Oscar made a 90. The weighting over here on that is going to be 0.5, so we're going to keep 50% of that. He made a 95, and the weighting over there is 3/10, so we're going to multiply by 3/10. And he made a 75 on his final, and the weighting is 2/10. So we crank out the math behind the scenes. Half of 90 is 45. 30% of 95 is, I'm way too tired for this. Like I just went kind of dumb, is going to be 31.5. And then 20% of 75 is going to be 15. So Oscar's final grade here is a 91.5, right? 91.5. It's not bad. I would have expected it to be actually lower than that. But the final was only 20% of his grade. Now, let's do Reagan's grades. All right. We have 50% of an 80, so 80 times 0.5, plus 30% of a 70, plus 20% of an 85. So that's going to give us 40 plus 21 plus 19. 61, which is an 80. An 80 on the money. So even though Reagan did a lot better on the final because of the weighting on the other things, her grade's actually lower than Oscar's. Bad grading skill, if you ask me. Now, if I was to actually multiply those two together, I would simply have a matrix over here. When I do this one, W times G, I would have a matrix that contains only two elements, a 91.5 and an 80. So something happened behind the scenes here. We took a 1 by 3 and we multiplied it by a 3 by 2. We kept the outside dimensions. We have one row and two columns. But as you can see, matrix multiplication is not about multiplying things in like positions, because you don't always have things in corresponding positions. There's a lot of work going on behind the scenes in matrix multiplication. So that's the gist of how matrix multiplication works. Time to do a couple of these. All right, below are square matrices A and B. Determine if the given equations are true for A and B. What conclusions can we make about the commutative property? The commutative property says, by the way, it says A times B is equal to B times A. This is true for things like numbers. Is 2 times 3 equal to 3 times 2? Yes, it is. Is it true for matrices? Maybe and maybe not. We can't say it always is. But anyways, let's do some matrix multiplication. We're going to do A times B, and this is going to be kind of a deal for y'all. Now, we are taking a 2 by 2. We're going to multiply it by another 2 by 2. So A contains the elements -2, 1, -1, 0, and B contains the elements -1, -5, 0, and 4. Now, we're going to end up with, since the insides match, it's good. The outside is our dimensions. We're going to have a 2 by 2. And the way you actually do these things is you think about your position. This is row 1, column 1. Knowing where you are in a matrix lets you do the math to do it. So row 1, column 1. Row 1 comes from the first matrix. She's -2 and 1. Column 1 from the second one, -1 and 0. We multiply across and add down. -2 times -1 is 2. 1 times 0 is 0. We add down, we get 2. Next up is going to be row 1, column 2. Row 1 is still -2, 1. Column 2 is -5, 4. I don't know why I put the slash in there. We are going to multiply across and add down. -2 times -5 is 10. 1 times 4 is 4. The sum is 14. Good stuff, right? It's really not. There's a lot of... after I do a couple of these, I start to get a little spatially disoriented. I can do these in my head, but I have chosen not to anymore. All right, let's think about where we are now. We're in row 2, column 1. So I'm going to grab row 2 from the first matrix. It's always from the first matrix where you get the row. You get the column from the second one. Remember, we multiply across and we add down. -1 times -1 is 1. 0 times 0 is 0. We add down, we get a 1. Now we're in row 2, column 2. So I'm going to grab row 2 again, which was -1, 0. Column 2, which is -5, 4. And I'm going to multiply across and I'm going to add down. Negative times negative is positive. 0 times 4 is still 0. We add down, we get a 5. Good stuff, right? Good stuff. So that is A times B. The question is it equal to B times A? So B times A, order's a big deal. We're going to put B first. -1, -5, 0, 4. And we're going to put A second. -2, 1, -1, 0. And we're going to go through with the algorithm, okay? First thing I'm going to find is row 1, column 1. So here, this row 1 is -1, -5. We're going to multiply it by column 1, which is -2, -1, and we're going to add down. Negative times negative is positive. Negative times negative is positive. 5 plus 2 is 7. Now I'm going after row 1, column 2. Row 1 is still -1, -5. Column 2 is now 1, 0. Remember, we multiply across and we add down. It's actually what we call, in other things, the dot product, so to speak. -1 times 1 is -1. -5 times 0 is 0. We add down, we get -1. Next maneuver, right here, is going to be row 2, column 1. So now we're going to grab this row, 0, 4. Remember, we multiply across. Column 1, -2, -1. And then we add down. 0 times anything is 0. 4 times -1 is -4. If you add down, you get -4. And finally, we are in row 2, column 2. So, still picking on 0, 4. Remember to multiply across and add down. Column 2 is 1, 0. 0 times 1 is 0. 4 times 0 is also 0. You add down, you get a 0. So, was A times B equal to B times A? No. And we are supposed to explain. So, the commutative property is not defined for matrix multiplication, which is actually given in your text, so I'm wasting time here. You'll notice that since A times B is not equal to B times A, we cannot do the commutative property. We cannot say it's true. Order is very important in matrices. Very important. All right. Below are square matrices A and B. Determine if the given equations are true for A and B. What conclusions can we make about the commutative and distributive properties? So this is going to be the distributive property. We're supposed to find A times A plus B and see if it equals AA plus AB. So I'm going to pause real quick and I'm going to work on this stuff. Well, you know what? I need to just go ahead and do it. Give me a second. Let me get ready. All right, so this is going to take a while. So I'm going to work on the left-hand side first. And, you know, be thinking about PEMDAS, kids. Please excuse my dear Aunt Sally. I need to figure out this piece first. What is A plus B? Well, A plus B is where we add like positions. -2 and -1 is -3. 1 plus -5 is -4. -1 plus 0 is -1. 0 plus 4 is 4. This is A plus B. I'm supposed to multiply it by A, which is -2, -1, 1, 0. And I'm going to try and do this in my head just to save room on paper. Okay? So a -2 times a -3 is 6. 1 times -1 is -1. 6 plus a -1 is 5. That was row 1, column 1. Now -2 times -4 is 8. Okay? 1 times 4 is 4. 4 plus 8 is 12. Now I'm on row 2, column 1. -1 times negative is 3. 0 times -1 is 0. I have a 3 when I put them together. Now I'm at row 2, column 2. -1 times -4 is 4. 0 times 4 is 0. The sum is 4. That's A times A plus B. Okay, that's what this is. This is A times A plus B. Now, I'm supposed to see if that's equal to A times A. So I need to do A times A. All right, -2 times -2 is 4. -1 times -1 is 1. 4 plus 1 is 5. By the way, this is going to be AA. Where was I? -2 times 1 is -2. 1 times 0 is 0, so -2. -1 times -2 is 2. 0 times -1 is 0, so I just get 2. -1 times 1 is -1. 0 times 0 is that, so -1. That's AA. I'm supposed to add to it AB. All right. Now I feel like I've already done AB. I got 2, 14, 1, 5. Let's just do it real quick. -2 times -1 is 2. 1 times 0 is that, so that's 2. -2 times -5 is 10. 1 times 4 is 4. 10 and 4 makes 14. -1 times -1 is 1. 0 times 0 is 0. 1 plus 0 is 1. -1 times -5 is 5. 0 times 4 is 0, so 5. Yeah, cool, we got the same thing. Now if I add these together, 5 and 2 makes 7. -2 and 14 makes 12. 2 and 1 makes 3. -1 and 5 makes 4. We're off a little bit, aren't we? Let's see if that was a mistake Milbrath made. I had a 5 up here. This one has a 7. Let's see here. This was A plus B. -3. -4. -1, 4. -2 times 3 is 6, right? One times -1 is -1. I got a 5. Oh, well, no. No, it's not the same. I am surprised. Pause real quick, see where I made a mistake. Okay, I found the mistake. It was right here. Negative 2 times negative 2 is 4. I probably got spatially disoriented. Negative 2 times negative 4 is 4. 1 times negative 1 is negative 1. You put them together, you get a 3. 3 plus 2 is not 7, it's 5. I knew I made a mistake because I was pretty sure about this. It's just been a minute. But what we just learned is these are the same. So we can say that the distributive property is defined for matrices. Milbrath just made a mistake. Sorry. It happens. All right, determine whether each equation may be true for the following matrices. Find if possible. So lots and lots of little things going on in this one. Nothing I can really do about that. But can we do A times B? So think about your dimensions. A is a 2 by 2, and we are wishing to multiply it by B, which is a 3 by 2. No, 3 by 3. So the outside does not match. Multiplication is undefined. We have what we call a dimension mismatch. Okay? The outside is undefined. All right. B times D. B is a 3 by 3, and we wish to multiply it by a 2 by 3. And hey, we're good to go. The outside matches. The result is a 3 by 2. So the resulting matrix is going to be a 3 by 2. So let's go ahead and work with it. We're going to have 3 rows, 2 columns, and this is going to be a bit of a pain in the old butt. We're going to grab row 1, column 1. Sorry. I wrote the numbers backwards. No, 2 rows, 3 columns. Forgive me, kids. I don't know if it's the headache or what, but it's the inside that doesn't match. You can't do B times D. I know we can do part 3, but B times D is a 3 by 3, and D is a 2 by 3, right? 2 rows, 3 columns. So the inside does not match. Cannot be done. Cannot be done. All right, D times B. D is a 2 by 3, and we're seeking to multiply it by B, which is a 3 by 3. So here we go. This is defined because the insides match. The result is a 2 by 3. And it is going to be a pain in the butt. So B times D, we're going to take row 1. Sorry, D times B, we're going to take row 1 and multiply it by column 1. So think about what goes here. Row 1 is 2, 1, 5. Column 1 is 2, 1, negative. There's a 0 there. 2, 1, 0. Remember, we multiply across. Order is extremely important, and we add down. 2 times 2 is 4. 1 times 1 is 1, 0. 4 and 1 makes 5. Now we are in row 1, column 2. So I'm still using 2, 1, and 5, but I'm using this column. 2 times 5 is 10. 1 times negative 1 is negative 1. So 10 minus 1 is 9. 5 times negative 3 is negative 15. 9 minus 15 is negative 6. Now I'm in row 1, column 3. Row 1, column 3. 2 times 1 is 2. 0, 10. 2 and 10 makes 12. Now I'm in row 2, column 1. So this is my row, this is my column. 0 times anything is 0. 0 times anything is 0. 1 times 0 is still 0. Now I'm in row 2, column 2. Still this row, this column. 0, 0, negative 3. Now I'm in row 2, column 3. 0, 0, 2, because 1 times 2 is 2. There you go. Wow, I'm already mentally exhausted. Probably because I'm trying to do it in my head. All right, more try-its. Determine whether each equation may be true for the following matrices. Find if possible. So we're supposed to do E times A and A times E. So E times A is where we take a 3 by 2 and we multiply it by A, which is a 2 by 2. The insides work, that's checked. The result is a 3 by 2. And order is so important. We're going to have 3 rows and 2 columns. So we're doing E times A. So row 1, column 1. 4 times 4 is 16. 0 times 3 is 0. There's a 16. Row 1, column 2. 4 times negative 1 is negative 4. 0 times 2 is still 0. 4 plus 0 is negative 4. Sorry, negative 4 plus 0. Now I am in row 2, column 1. Here's row 2. Here's column 1. Negative 2 times 4 is negative 8. 1 times 3 is 3. Negative 8 plus 3 is 5. Row 2, column 2. Negative 2 times negative 1 is 2. 1 times 2 is 2. 2 plus 2 is 4. Row 3, column 1. 0 times 4 is 0. 3 times 3 is 9. Row 3, column 2. So that's going to be this row, that column. 0 times negative 1 is 0. 3 times 2 is 6. Now, the next step is A times E. A times E is a 2 by 2, and you're going to multiply it by E, which is a 3 by 2. The inside says no, dimension mismatch. Good stuff, bruh. Good stuff. All right, what's up next? We have a 3 by 3 and its identity matrix. So we're going to multiply this guy by that guy. And by the way, this is called an identity matrix. So do not be surprised at what happens. All right, so I'm going to do a little bit of this by hand. We're taking a 3 by 3 and we're going to multiply it by a 3 by 3. The insides match, we're good to go. The outside is the dimensions. Think about your position, row 1, column 1. Row 1 is going to be 1, negative 3, 2. Column 1 is 1, 0, 0. 1 times 1 is 1, 0, 0. And we add down and we get a 1, which is exactly what we had. Remember, this is called an identity matrix. All right, row 1, column 2. So I'm still this row, 1, negative 3, 2. Now I'm this column, 0, 1, 0. 1 times 0 is 0. Negative 3 times 1 is negative 3. 2 times 0 is 0. I add down, and I get negative 3. Well, I'll be darned, it's the same thing. Let's do this one more time and see if it keeps working. Now I'm in row 1, column 3. Row 1, again, is 1, negative 3, 2. Column 3 is 0, 0, 1. I multiply across, and I add down, and no surprise, I get a 2. It's called the identity matrix. If you multiply a matrix by an identity matrix, you get the original thing back because it is the matrix equivalent, at least when you're doing multiplication, of 1. So anywho, I'm not going to waste any more time on this. If you're still lost as a ghost, go back and rewatch what I just did. All right, what is the product of these two things? Well, first off, this is an identity matrix. So if you multiply anything by an identity matrix, you're just going to get the thing right back. This guy is actually a rotation matrix. What it's doing is it's multiplying things by negative 1. So it's actually worth exploring. So if we take a 2 by 2 and we multiply it by 2 by 2, we're going to get a 2 by 2 back. Row 1, column 1. A times a negative 1 is negative 1. B times 0 is 0. So sorry, that's negative A plus no B. Negative A. Row 1, column 2. A times 0 is 0, B times -1 is negative B. It changed the signs, didn't it? Kind of cool. Row 2, column 1, C times -1 is negative C, and then D times 0 is 0. Row 2, column 2, C times 0 is 0, D times -1 is negative D. This guy was the equivalent of multiplying by -1. It was the equivalent of doing that. It's actually performing a rotation. It's actually rotating things across the origin. That's what it's doing. That may or may not make sense to you. I don't know if it does or not. That's just what it is. All right, fun lesson. Kinda.